Fusion reactor. If two deuterium nuclei charge plus E mass 3.34 times 10 to minus 27 kilograms get close enough together, the attraction of the strong nuclear force will fuse them to make an isotope of helium, releasing vast amounts of energy. The range of this force is about 10 to minus 15 meters, that is femtometers. This is the principle behind the fusion reactor. The deuterium nuclei are moving much too fast to be contained by physical walls, so they are confined magnetically. Part A. How fast would two nuclei have to move so that in a head-on collision they would get close enough to fuse? Assume their speeds are equal, treat the nuclei as point charges, and assume that a separation of 1 times 10 to minus 15 meters is required for fusion. So we have two deuterium nuclei, charge plus E, moving with the same speed v towards each other to encounter a head-on collision. The charge Q is once again plus E for each deuterium nuclei, and the mass is given in the problem statement as 3.34 times 10 to minus 27 kilogram. So let's say that they were at infinite separation initially, and their final separation will be 10 to minus 15 meters, which is the range of the strong nuclear force, so that they will fuse. Now, what is going on in this problem? Well, from infinite separation, as they come closer, they're going to encounter a repulsive force due to the Coulomb force between them, and that's going to slow them down. So we want them to stop at a distance of 10 to minus 15 meters so that the strong nuclear force will take over and cause them to fuse. Now, the initial potential energy plus the initial kinetic energy is equal to 0, because we are at infinite separation initially, and the initial kinetic energy is 1 over 2 mv squared, assuming we're not talking about relativistic limit here. So non-relativistic speeds multiplied by 2. This should be equal to the final potential energy plus the final kinetic energy, and because I'm going to assume that they will stop at 10 to minus 15 meters, the final kinetic energy will be 0. What is the final potential energy? It's going to be Coulomb's constant, the charge E squared divided by R final. K, Q1, Q2 over R is the potential energy, electrical potential energy. Okay, so this means that I'm going to have mv squared, the total kinetic energy, initial kinetic energy, equal to the total final potential energy, Ke squared over R final, which means that the speed has to be Ke squared, Coulomb's constant, charge, electron charge E squared, divided by mass times R final square root. So this is the speed I will need, and I can calculate what that speed should be by plugging in the numbers. So I'm going to have, for Coulomb's constant, 9 times 10 to 9, and for the electron charge, 1.6 10 to 1.6 10 to minus 19 coulombs squared, divided by 3.34 times 10 to minus 27 kilograms times our final 10 to minus 15 meters, and all this inside the square root. So we will obtain a final speed. The final value for the speed to be 8.3 times 10 to 6 meters per second. And there's one more thing to check here. This speed is actually much less than the speed of light, 3 times 10 to 8 meters per second. So our non-relativistic treatment actually holds for this experiment. Part B. What strength magnetic field is needed to make deuterium nuclei with this speed travel in a circle of diameter 2.5 meters? So I have deuterium nuclei, charge plus E, moving with this speed v in a circle inside this uniform electric field that's pointing into the page. Now the Lorentz force V cross B, so you have your right hand forefingers pointing in the direction of velocity and then curl them towards the magnetic field into the page. The thumb points radially inward. That's the centripetal force responsible for this circular motion. The magnetic force FB, the Lorentz force, is Q cross product of velocity with the magnetic field, where the magnetic field B is uniform and it points into the page. That's the direction of the uniform magnetic field. Okay, so the centripetal force Fr is EVB, and it's basically pointing radially inward, which is equal to mass times the centripetal acceleration mv square over the radius of the circle, which is the diameter d divided by 2. So these v's will cancel, and I will find EB is equal to 2mv divided by the diameter d, so that the magnetic field magnitude is 2mv divided by E times the diameter d. That's the magnitude of the magnetic field we need to obtain this speed. So F sub r, once again, is my centripetal force responsible for the uniform circular motion, UCM. Okay, so let's plug in the numbers. For the magnetic field, I have 2 times mv, so 2 times 3.34 times 10 to minus 27 kilograms times the speed I need, 8.3 times 10 to 6 meters per second, divided by 1.6 10 to minus 19 coulombs, the electron charge, multiplied by the diameter d, which is 2.5 meters. So this gives me a final value for the magnetic field magnitude, 0.14 Tesla. That's the amount of magnetic field needed to move these deuterium nuclei with the speed in a uniform circular motion inside the uniform magnetic field pointing into the page. Okay, so we're talking about the fusion reactor. Two deuterium nuclei, when they come close enough, which is close enough is femtometers, they will feel the strong nuclear force which will make them fuse to release lots of energy. That's the principle behind the fusion reactor. If they start at infinite separation and move with the same speed towards each other, they will, in order to make sure that they're going to encounter the strong nuclear force, there is a minimum speed that they must have to make sure they will get close enough. And during this experiment, they will feel repulsive force between the two charges. So the initial mechanical energy will be equal to the final mechanical energy. The system is isolated in terms of energy. The initial potential energy is zero at infinite separation. Final kinetic energy is zero because they will just stop at 10 to minus 15 meters. So 1/2 mv squared times 2 using non-relativistic kinetic energy is equal to final potential energy, Coulomb's constant kq1, q2 over r, ke square over r final. We find that the speed we need is square root ke square over mr final. The numerical value is 8.3 10 to 6 meters per second. Then we check it with the speed of light, which is 3 times 10 to 8 meters per second. It's 2 orders of magnitude less, so we can say that the non-relativistic approximation holds. So kinetic energy is indeed 1/2 mv squared. What magnetic field do we need to have this speed on a deuterium nuclei moving in a circle? If the magnetic field is pointing into the page, the velocity, tangential velocity, is directed in the counterclockwise direction, with the right hand forefingers pointing in the direction of velocity, curling down towards the magnetic field into the page. The thumb points radially inward, which is our centripetal force, Fr. So EVB, because of the 90-degree angle between them, magnitude of B sine 90, that is 1. EVB is mv squared over r, where r is the diameter, which is r is the radius, diameter, divided by 2. So 2 mv over d is EB. So B is 2 mv over ED. If we substitute the numbers, the magnetic field we need is 0.14 Tesla.